from CYSEC, Yannick Roelvink. Yannick is an R&D engineer at CYSEC, so within the innovation team at CYSEC, and you are organizer of CYSAT. Yes, you were last year. I remember you speaking. So CYSEC is based in at the EPFL Innovation Park in Lausanne, Switzerland. At CYSEC, you are working on a variety of different projects. We detailed one of them, but you focus on mainly on cybersecurity implementations for embedded system, edge computing, IoT mostly, and satellite communication. Most notably, you currently work as a lead engineer of the prototype in front of your laptop development for CYSEC's newest product, so ARCA Satcom, the object of your presentation today, which aims to provide a multi-orbit plug-and-play and gateway-agnostic solution for encrypting satellite internet connections while providing enhanced throughput as compared to standard VPNs. You hold a bachelor's degree in applied physics from Delft University of Technology and a master degree in aerospace engineering from ISAE Superior, Toulouse, with a specialization in embedded system. Yannick, the floor is yours. Sorry, again, if you want to ask any question, please connect to ConnectMe and use CYSAT 2023 as code.
Thank you very much, Julien, for this introduction. Yes, thank you all for being here today. I will be talking to you today about combining security and performance in geostationary satellite links. So during the next 20 minutes or so, there's a few different topics that I'd like to discuss with you. First of all, I'd like to introduce the general problem. Why is it an issue, or why is it difficult to combine security and performance in geostationary links? The main question, why am I here today talking to you about it? Secondly, I would like to talk about some use cases. Where do we see that there is an interest for us to have both security and performance at the same time? And where do we see the biggest improvement from the current solutions that exist? Secondly, I would like to introduce our proposed solution, as briefly introduced by Julien, indeed ARCA Satcom, for which I am the lead engineer at CYSEC, where we aim to provide security in geostationary satellite links while minimizing the impact on throughput performance. Afterwards, I have a few demos planned. Of course, the main reason we're all here in the French Tech for some actual demos to see how the solution works, rather than me just talking about it. And lastly, we will have some time for some questions. Of course, feel free to ask some questions during the presentation as well. We have some moderators that will take care of those. So let's get started. First of all, the problem description. Why are we interested in the issue? Why are we talking about geostationary satellite communication, security, and performance? And the question, the answer, why don't we just do both, is less straightforward than we might think. So, first and foremost, I would like to discuss why is this still an issue? Why is it a problem to combine cybersecurity and performance in geostationary satellite links? Well, we would think that in general, all satellite communications are encrypted, right? That's a little bit what we expect when we use very high confidential data over satellite communication, that we think it is secured. But you would be wrong. As James Pavour presented at CYSAT 2021, it is actually possible to hijack and eavesdrop satellite communication data with less than 300 euros worth of equipment. A specific example for this is, for example, that the team of James Pavour at Oxford University, they were able to acquire WinTin login credentials for a management software for a wind farm, but also more critically, the full inbox of a defense lawyer in Spain that was forwarded by accident over a satellite link. Of course, this is information we don't want to be out in the open, and this shows that there's a general assumption that we assume that satellite links are secure, whereas this might not be true at all times. A second example could be the hack of the VSAT infrastructure last year. Of course, I know there will be a lot of talk about this specific attack during this session of CYSAT, so I won't be diving too deep into it, but this can show that there's not only a cybersecurity issue related to links, but also a cybersecurity issue related to the infrastructure and the hardware itself. What we're trying to achieve here is try to provide cybersecurity for both of these at the same time. But why can't we do that while also providing performance? The main issue originates from the fact that the cybersecurity implementations, such as a VPN, And the performance-enhancing systems that are used in geostationary satellite systems to enhance the performance of the throughput, such as a performance-enhancing proxy, or PEP for short, are simply not compatible with each other. In the most general sense, performance-enhancing proxy will need to access information of the satellite link, of the data packages transmitted over the link, in order for it to improve the performance. For anyone interested how that exactly works, we can discuss about that more in detail. Right now I won't go into too much detail regarding that. Whereas a VPN encrypts all of this data. So in general, when you combine VPN and performance-enhancing proxy, you will see that the performance drops very quickly, as simply the performance-enhancing proxy is not able to boost the performance of the packages that are encrypted via VPN. There are some, because of this, many internet service providers, they try to aim for the highest possible throughput. So this is something that the clients want. They want, when you look at this internet service provider, they say, oh, I give 50, 100 megabits per second. Perfect, we go to you. And then we don't mention the cybersecurity implementations, as we know that they cannot be compatible. There are exemptions. We have a few internet service providers that implement governmental security implementations where they do aim to provide a level of cybersecurity over geostationary satellite links, but these are either expensive, have very low bandwidth, or are very difficult to achieve and to implement into existing infrastructures. So for us, at CYSEC, we saw this challenge. Together with the ESA ARCTES program, we started the development of a product that is able to supply cybersecurity, performance, and easy integration into existing infrastructures. Where do we see this specific implementation to have the most amount of impact? For example, in situations where either we do not trust or we do not want to trust existing terrestrial links, or where we simply do not have any. If I take, for example, the humanitarian aid and diplomatic networks example, if we have an embassy in a country that we do not trust, or where we do not want to trust the specific infrastructure they have laid out for the internet, we can simply connect ourselves to a geostationary satellite communication link, use that link to, for example, do a video call to another embassy or to the home country, but we do want to be sure that this specific communication is secure. Of course, for such video call, we need high throughput while ensuring the security of the link itself. Similar examples exist for planes and maritime implementations, but there, of course, we simply do not have a terrestrial link, so we are sort of limited to the options as to how we can connect to the internet. Now that we have discussed a little bit the problem in itself and the specific implementations where this could be interesting, the main question is of course, okay, but how do we do it then? How, if I say that it is not possible to simply combine a VPN with the existing performance-enhancing proxy, how do we do it then? This is where ARCA Satcom comes into view. This is a project developed under the scope of the ESA ARCTES program by CYSEC with the help of Arma Suisse, thank you, where we have developed a solution where we are able to provide both cybersecurity and performance at the same time. So it consists out of three main components. We have a software package, a performance-enhancing proxy, which is based or forked from the existing solution called QPEP, developed by Oxford University. What we have done there is we have taken this specific software package, we have added additional security features, and we have started testing it inside real use case scenarios. Secondly, we have developed a hardware module called the ARCA router, for which I have brought one with me today, in which we deployed this specific software module to start the communication on the client side of the satellite link. And then on the other side of the satellite link, we have the ARCA server, which does the same, but then to receive the data and to decrypt it and ensure that all is right. To see this in a more implementation-wise example, this is the general overview of how we envision the implementation to be implemented. We have a user all the way here that wants to connect to the satellite internet and wants to do so in a secure way. He connects via a TCP connection to our ARCA router, which is this, for example, this module that I have here with me today, which then the performance-enhancing proxy starts communication over a secure quick connection to the other side of the satellite link, ensuring both security and performance at the same time. And then We have on the server side a connection that receives the information, decapsulates it, decrypts it, and sends it to the eventual destination of the internet connection itself. If we then zoom in on the performance-enhancing proxy, what we have done is we have added the security layer during the performance-enhancing itself. And how have we done that? Is we have enabled the QPAP module developed by Oxford University to be compatible with hardware security modules, such as, in our case, a trusted platform module on the router side, and a hardware security module, or the bigger version of a trusted platform module, on the server side. This ensures that we are able to host a high level of security with a hardware root of trust for the complete communication. I've already gone into this. How we have done this is we have integrated the performance-enhancing proxy inside ARCA Embedded. ARCA Embedded is a trusted operating system developed by CYSEC specifically for ARM devices, which enhances the cybersecurity level of the device itself with an integrated key management system. This key management system is also developed by CYSEC to communicate with a trusted platform module. So when we do a key exchange, when we do an encryption, the key storage and the key generation is all done by the hardware itself. And then the performance-enhancing proxy simply takes those keys and uses it to perform the key exchange afterwards. Combining the key management system, the operating system, and the trusted platform module in the ARCA router provides it with several security features inside the specific device, such as a secure boot chain to ensure that only devices signed by us and trusted by CYSEC are allowed to boot on the device. We have an immutable file system, which means that the file system files are read-only. After initialization in the beginning, they cannot be changed, so no tampering possible there. We have a seamless system updater, which ensures highest possible uptime, which means that we can update in the background while the main system is running in the front. We have full disk encryption, which of course, while the device is off, ensures that no memory can be accessed in the device. We have our own proprietary key management system, and as I mentioned before, we have a hardware root of trust, either a TPM or an HSM, for anything related to key storage and key generation. Going to the other side of the link, of course, we encrypt and encapsulate the TCP packages in a quick frame on the one side of the satellite link, but then we have to, of course, receive, decrypt, and decapsulate it on the other side. So in that sense, we have ARCA server, which is sort of a bigger version of the ARCA router, doing exactly the same, but in the opposite way, in reverse. The advantage of the ARCA server is that we can run this on a decentralized manner, running either on-prem or on-cloud in a cluster or not, giving us the possibility to host multiple server instances at the same time on a single hardware module while utilizing a key management system and a hardware security module as we would on the router side with the TPM. Combining the router, the performance-enhancing proxy, and the server into a real-life application gives us the possibility to assess the performance of this specific implementation. So that's exactly what I have done using a real geostationary satellite link. And what I've done is I have taken the data from the plane connection, so when we don't encrypt at all, I've put that at 100%, and then I evaluated our solution and a standard VPN to see how much they would compare in terms of full bandwidth occupation compared to a non-encrypted solution. Basically, when we look at this figure, 100% would mean no encryption at all. When we don't have any encryption at all, we would be using 100% of the data link. When we ensure, when we add additional security, we have a loss of performance because we add overhead. So in our case, the ARCA PEP module in blue is able to occupy roughly 30% of the network band while providing high levels of security at the same time. Whereas, for example, OpenVPN, an example of an alternative solution, is only able to achieve around 13. This shows us that we, providing a higher level of security than a software-based library such as OpenVPN, are able to also achieve higher levels of performance at the same time. That was it for the most talking part of this presentation. Now, of course, the main reason why we're all here, I have a little demo to perform here today. So what I did is I brought one of the ARCA routers with me today. And what I would like to do, if you guys want to try, if you open your phone or your laptop or anything related to that, you can see that in the network list, there will be a network hosted by this specific router called CYSEC ARCA router R1. If you want to connect to the Wi-Fi, this is the specific Wi-Fi password. Unfortunately, due to the fact that a satellite link did not fit in my backpack today, I could not bring the full satellite link with me, but we are able to check the user experience once we connect to the router itself. And then afterwards I have a few videos of how the performance-enhancing proxy works on a real geostationary satellite link. So what I can do is I can show this actually myself when I go to the network. And I go to, this is a bit complex like this. Well, unfortunately you cannot see that, but I'm changing my network now to the router. And I am then going to you will see that I can log in to, or I can access our own graphical user interface of the router hosted here. You can verify this yourself. If it doesn't work at the moment, we can check it on the booth afterwards, as of course I'm not going to spend a lot of time debugging at the moment. Basically, we have the access to the router here right now. I can then log in. And then once we're logged in, we can see the general idea that a user would have when it's using our specific solution. It will have the ability to enable or disable the performance-enhancing proxy, either enabling or disabling the secure connection over the satellite link. It will have some status information. Is the satellite link working? Is the server running? And is the secure key exchange required for the secure communication well performed? And we have some statistics related to the speed and the ping for us to debug in case there is any issue to the implementation. Of course, as you can see, I'm not connected to anything right now, so we don't have any internet connection. But in general, when we are connected, we can, as soon as I launch the PEP, it will automatically perform the key exchange and give us all the information related to that. Then I have a bit more of an actual implementation. What I've done is I have done tests over real geostationary satellite links, and I will show you exactly what would happen when I connect this specific router to a real satellite link, flip the switch to enable the performance-enhancing proxy, and then. So on the left-hand side, we will have a video. On the left-hand side, there will be a terminal of my laptop, which will be connected via the internet, as we saw before, to the router, and which will imitate the commands that the GUI would send to the backend in order to launch the performance-enhancing proxy. And then on the other side, I will have a monitoring program which will show us exactly what is happening with the performance-enhancing proxy itself. Basically, what will happen is I will then launch the monitoring program on the right-hand side and the GUI command on the left-hand side to start the key exchange over the geostationary satellite link. And then afterwards, you will see that I will be able to reach the internet over geostationary satellite link to then access the CYSAT website. This is really to show that once you actually flip the switch on in the GUI for the performance-enhancing proxy, this is what would happen behind. Of course, well, we all know the website by now. And then when we dive one level deeper to actually see what happens behind it, to see the full key exchange, we have three main parts. So, in order to explain a little bit what we're seeing, bottom left, everything on this side is the router. Everything on the other side is the server. What I have is I have my performance-enhancing proxy running here on the router side and here on the server side. And I have a key management system running on the router side and on the server side. And what we will see is, at first, I will launch the connection and it will say, okay, I will verify if the internet is online. Can I actually connect to the server? It then says, okay, perfect. Once I'm connected to the server, I can start generating the keys. So here the key management system says, I received a request. Let me handle it. I will generate a key for you. It will then start generating the keys on either side, you can see a lot of information happening. This is the key management system telling me, okay, I generated a key, a public key, I generated everything related for the symmetric key encryption. Then the other side, it was a bit quick. The other side receives the request, says, okay, I'll do the same. And then afterwards you can see that the two communication channels at the bottom, they start communicating and send packages back and forth. Thank you very much for coming here today. I have one last slide. If you're interested to test out this solution yourself, or if you're interested to see how it works more in detail, we have a pilot program started up where we will send you one of these boxes to test it out yourself. Should anyone be interested. If you're interested, please go see us at the booth and we can discuss a little bit further. Thank you very much.
Thank you. We have few interesting questions on architecture, key management, and crypto. Maybe I read the first one. Maybe on where is it? Yeah, on architecture. So, do you plan to support one other architecture of ARCA Sat apart from ARM?
So yes, we actually have also, that's a very important question, which I actually failed to mention, but on the server side we have an operating system running on x86, which is also a version of the secure trusted operating system that we developed at CYSEC. So it's not just ARM, this board specifically is running x86 at the moment, where we are able to also deploy it in a similar way.
Okay. Still in architecture, where is the ARCA server for the decryption located? Is it on the client side to achieve full end-to-end encryption?
So this depends, of course, on the specific implementation that we have in mind. The ARCA server can deploy it anywhere where we want. It can be the actual final destination server if we want full end-to-end encryption. It can also be in a centralized manner if we just want to ensure secure communication over the satellite link and that the rest of the link we trust. This is of course up to the user. In general, if you have a server, we can host ARCA server and ARCA Trusted OS on it.
Okay, few crypto question.
Ah, perfect.
Yeah. On key management and authentication. Yeah. First one, how does the key update cycle look like, and how often do you change?
So for the moment, for everything related to key updates, what we have is we have a rekeying system set up that we trigger after a certain amount of time. For the moment, we set it to 1 hour, but this is configurable according to the needs of the client, where we where we start the second communication channel, where we do the same key exchange procedure. We continue communicating on the first, and then as soon as the second communication channel is ready, we stop the first and we redirect all the data over the second. Thank you, that's a good question.
Last one I have on ARCA router. Do you use X509 certificate asymmetric keys to secure the identity of the ARCA routers before?
So we do actually at the moment ensure the identity of the ARCA servers. So what we do is the ARCA router sends a request to an ARCA server. The server then replies saying, okay, perfect, I received your request, here's my information. And with it, there is indeed an X509 certificate to ensure the identity of the server. For the routers itself, we have to see, but for the moment, it's the servers that are more important, because we, of course, want to ensure that we are communicating with a secure server rather than one that imitates to be one.
Okay, thank you. We still have 3 minutes for questions in the room, if you don't have the application. You have to use the mic for people online.
Wonderful, thank you. You mentioned that the ARCA router is using full disk encryption, and I was wondering if you could talk a bit about how the boot sequence works and how the keying works for that.
It's a very good question. Personally, I'm not involved in the development of the boot security systems. We have our expert for that related to the embedded systems. What I can do is I have some additional slides where I can explain a bit more into detail the exact implementation for the boot sequence and everything, but I do not have them with me here right now. So what we can do is our expert is here today as well, and we can discuss this directly at the booth afterwards. But thank you, very good question.
Great, thank you.
Yeah.
Another question, maybe last one. Sorry? I have one online actually. Let me. So, do you plan for a rather hard, radiation problems, TPM solution for flight?
So, This specific solution is not made for implementations inside the satellite itself. So for radiation hardening TPM solutions in flight, this is not in the scope for this specific solution, as our solution remains on the ground. We simply use the satellite as a relay to relay our communication to the other side of the network. So this is not really what we're aiming for at this point, no. We have, however, a second solution whose presentation will be tomorrow, related to all cybersecurity to the satellite itself, rather than using the satellite as a relay, which will be tomorrow morning in the same room here, provided by my colleague Louis, which is a bit more related to this topic, I think.
So see you tomorrow.
Yeah.
Okay, thanks a lot. Thanks for the question. Time's up.